And first of all, I'd like to thank Dr. Urs and Dr. Koch for the invitation to be here with all of you today. It's a great symposium. I'm really enjoying it. So today I'm going to talk about some of the work that we do at our center with deep learning and data-driven models for the prediction of extreme events. I will also show you how this prediction can be used to implement a climate adaptation strategy. All right, let's start with the outline of my talk. We start by describing atmospheric river, which is the main atmospheric phenomena that we study at our center. Then I will talk about the climate adaptation strategy that we've been working on, which is called the Forecast-Informed Reservoir Operations Program. And then I will dive into the strategy that we're using to improve our ability to predict extreme events, which include a very large ensemble based on a physics-based model, a deep learning correction in a post-processing framework of that ensemble, as well as the new AI the potential of the new AI data-driven models that we've been hearing about it today. All right, let's start with atmospheric rivers. As Professor Xu was mentioning this morning, this is actually a very dominant weather phenomenon over the western US and many other areas around the world. They are very long, elongating transport of humidity, so they are a combination of humidity winds that are about 800 miles long, so 1,000 or more kilometers long, wide 300 to 400 miles, and they are confined the last 3 to 4 miles of the atmosphere close to the ocean. It's a transport, it's literally a river in the sky, and they are the equivalent, they move as much water, for example, as the equivalent of the water that 25 Mississippi rivers send into the Gulf Coast. So a really massive phenomenon. When the atmospheric river lands over land and interact with the topography, it creates precipitation in rain and snow. And when it gets to climate projection, I'm not going to say much about it today, about atmospheric river, but what is important to know that there have been regional study for regional climate over California. What has been estimated that it could happen is that the most intense storm is going to increase in intensity and frequency, whereas the less intense storm is going to decrease their frequency. So the average annual precipitation over California is going to be very similar, but it's going to be generated by less and more intense storms. So that's what we have to face to adapt to climate. So in this diagram here, you see the impact of atmospheric rivers over the western US. In red here, the dots represent the percentage of damaging losses that can be associated to atmospheric rivers. This is data based on 40 years from the National Flood Insurance Program. And as you can tell, especially over California, over the coast, but also other areas, the percentage, most of the damage is actually associated with atmospheric rivers, upward on 95% or higher. If you calculate over the 11 states of the western US, 85% of the losses actually can be associated to atmospheric rivers. So this is a very large portion, just to show how important these storms are for this area. For example, in this image where you're seeing here the catastrophic impact on atmospheric river intense precipitation on an area where there's been a wildfire. On the burn area, that create post-fire debris flows, which in this case in January 2018, unfortunately caused 23 deaths and several hundreds of homes actually destroyed in the Montecito area in California. So that was a very impactful storm. And as I said, not only in California, many areas around the world. All right, let me talk a little bit about the climate adaptation strategy that we are implementing over the western US. It's called Forecast-Informed Reservoir Operation. Basically what is it? It's a strategy to better inform the decision to retain or release the water from a reservoir by adding additional flexibility to the way the reservoir is managed, and I will show an example of that, by leveraging the information that is provided by observation and improved weather and water predictions. It's a very collaborative effort which includes folks from the academia, from local and state authorities, as well as agencies that are managing the reservoirs. It's very interdisciplinary. There includes expertise from atmospheric science, hydrology, observation, verification, and water resources engineering. And the key aspect of it is to bring people that have stakes at a specific reservoir to the same table to discuss solution that works for everyone. Here you see an example. Actually, this is the same lake that Professor Xu was talking about this morning that was impacted by a very impactful atmospheric river in California. And here you see the issue that we have in California is that, for example, in the bottom left image at the beginning of the water year, October 2021, the lake was very low, was at 27% of capacity. At the end of the next water year, in June 2023, the lake was back to full capacity, 100%. That's the issue that we face in California, and I will show you why that is important, which basically the average weather in this area of the world never happened, or I should say, doesn't happen very often. What that means that often we have either very dry years or very wet years. Let me show you why that is an issue. All right, this is the concept of the FIRO program, how it works at a specific lake. Here, showing an example of Lake Mendocino, which is the first place where we test this technique. Lake Mendocino is just north of San Francisco in California. Basically, what you're seeing here is the storage, supply storage of the lake at any given time during the year. Does this work? No, all right. I can do without it. So the dashed line is called the curve rule. That tells the manager of the reservoir how much water they can keep at the reservoir at any given time, right? So that curve was designed when the reservoir was built, which it was several decades ago, 30, 40 years ago, more. And so it's based actually what was the best knowledge of the weather back then, which is climatology. What is climatology? Climatology is the average weather. So on average in California, you have rain in the winter, in the spring. And so the idea there is to prevent flooding is that in November, the reservoir is emptied, is brought it down to a level of 70,000 acre-feet, which is a volume measurements. It's kept low throughout the winter up to March, and then in March and in the spring, the manager is allowed to fill in back with the spring rains the reservoirs. Now, what is the issue with that? For example, you see here in red, you see what happened in the water year 2013, that the manager did keep the reservoir very low until the end of November. Then there were two atmospheric river storms that quickly filled up this watershed and this reservoir. And then what the manager had to do at the end of December had to release water to go back to the rule curve, right? That's what that was mandated to follow. It kept it low until the end of March, then hoping for new rains to come. But then the rain never came. That happened to be a dry year. And so actually there's been when started a few years of droughts. And so that created, lost a lot of water that could have kept. So the idea of FIRO is very simple, actually. If we could keep more water into the reservoir by looking at the forecast, every day we can look at the forecast, right? If there is not a storm coming, the water manager could keep that water, right? Doesn't have to release it. And if he trusts that forecast, can do that every day. And if you do that, you might end up at the end of the year to actually save quite a bit of water. So the difference there between the green dashed line and the red line, it's actually enough water that would serve 20,000 homes over a year. So it's quite a bit of water. We're talking about you could say between 10 and 30%. So we actually, at this reservoir, we ended up implementing this strategy for the real operation of the storm. So I'm going to show you two examples of how that worked in a real scenario. So here now you're looking at water year 2020. That was a very dry year. And so what you're seeing here in this diagram, the bottom dashed blue line is the old rule curve, whereas the top blue dashed line is the new rule curve that we modify based on our understanding on the forecast skills and the forecast accuracy and the trust we have in the prediction at this specific location. And so what you're seeing there that because we changed the rule curve, now the operator is basically it's been following the black line. As in January, the storm keep filling the reservoir. It could keep the water until the level of 80,000 acre-feet, which is the new level the new floor that we raised it from 70,000. But if he would have followed the old curve, that would have been the red line. He would have to empty the reservoir actually right at the mid-December, keep it low by releasing water to follow the old rule curve. But because we changed it, it could keep much more water. Then, as I said, this was a drought year, so there wasn't any precipitation in the spring. Nonetheless, because of this strategy, we managed to increase the water supplies by 18%. So a great success, right? This is a dry year. Now, we also look at so this is actually an ongoing operational implementation of this strategy. Here you see the example of the year 2023. Very different situation. This was a very wet year. And now you see again there were storms, very, very intense storm that created inflow into the reservoir by mid-January. And so with the new rule, which is basically the top dashed line, the new inflow in the reservoir is the black line. So there were storms to keep the water up to 80,000, whereas with the old rule is the red line. You have to go down again to 70,000. And again, you follow how the two different strategy results in the inflow on the reservoir. What you also want to notice that we knew the change that we did. Not only we raised the floor, but also we anticipated when the manager can start to fill up the reservoir again, which is with the new curve, it's about mid-February. With the old curve, can only start by March to fill the reservoir. And so with this strategy, again, this example, we increased the water supply by 13%. So a great success. Now, to do all of this, I guess a key aspect that I want to underline here, we are dealing with a climate problem, the precipitation associated with atmospheric rivers, by utilizing the skill of weather prediction. So this is very important. Weather prediction are very skillful from 0 to 10 days, right? Whereas for climate projection, you need estimate, as we are this morning, all the way to 10, 20, 50 years, right? But we're dealing with a climate problem, leveraging the information that we get from weather prediction. So it's a very clever solution. I would say a very clever climate adaptation strategy. Now, the key aspect of all of this is to maximize the skill of weather prediction. So I want to show you what kind of work we're doing for that at our centers. First of all, we design a very large ensemble. It's based on a physics-based model, which is called Westworth. We do a 200-member ensemble. Just to put this in perspective, the global operational center right now, the European center, which is the leading center, as an ensemble with 51 members. The US system has 31 members, whereas we're doing 200 members because we're doing a regional system only over the Western US, and because we have a full supercomputer dedicated to this. Now, why do we do 200-member ensemble? The reason why we do that, because we care about extreme weather. So extreme weather are in the tail of the distribution, the right tail of distribution of precipitation. Everything else be equal, to represent well the tail, you need more sample. We demonstrated that. We actually, a paper out just came out on that. And so that is the reason why we do a 200-member ensemble. I'm going to tell you later how that is actually a place where the new AI data-driven model can help us a lot. But so here, I'm not going to go much into the details, but just I want to show you how we do this ensemble. And the other reason why we do the ensemble in general for weather prediction is because the atmosphere is a chaotic system. You cannot predict it deterministically. You need to look at most likely scenarios for any given event to try to represent the likelihood of different scenarios. So the way we do it, we use initial condition and boundary condition from the global model. We have a set of different 82 initial condition, boundary conditions. We combine that with stochastic perturbation to each of the 200 ensemble members. And then we include 100 distinct physics configurations, which goes back to the physics complexity that Yusuf was talking about earlier, where we combine different boundary layer schemes, different microphysics schemes, and different convection schemes. Actually, this goes back to what Steve was talking about this morning. Try to capture the uncertainties that stem from each of these schemes. And combining all this together, we have the 200-member ensemble. So let me show you how this system performs. First of all, an example. This was a very impactful storm at the end of, between the end of 2022 and the beginning of 2023. It was an atmospheric rivers. We're looking here at the time series at San Francisco. And what you're seeing here in red, the observation, black line represent the minimum and the maximum of the ensemble. The dashed line is the ensemble mean. And on the top left, you have the US system, the global ensemble forecast system, the bottom left, the European system, and the top right, our 200-member ensemble. And I want you to focus on the peak precipitation for this event, which is very intense. And here you see a good example of the benefit of the 200-member ensemble, right? We have a larger spread. It's actually capturing what actually is being measured, as shown by the red line, where the two global systems, the envelope of their ensemble did not capture actually what happened. I should say that, you know, we use the global system as a springboard. We use this system as initial condition and boundary condition to add additional scale with our system, which in this case worked out well. Now, you can actually assess very objectively, in a very robust way, how skillful these systems is. This is an example of doing that. A very important attribute of this probabilistic system is the spread-skill relationship. One way to assess this is to compile this diagram, the bean spread skills plot, where if you have a perfect ensemble on this diagram, you want to be on the one-to-one line. So you're seeing the performance of the three systems, the two global system, the European one in green, the US in blue, and our system in red for day 1 prediction, day 3, and day 6 over a 10-month period spanning 2 days. So this is a very robust assessment of the performance of this system. And as you can see, our system does really well, actually does better than the global system. It's significantly closer to the one-to-one line. For day 6, actually, it's almost perfect, very close to the one-to-one line. But you can tell at day 1, day 3, there's still a lot of room for improvement. That's where AI and machine learning can play a big role, to add skill to the initial estimate, to the first guess from the physics-based model. So let me, before I go to that to show you how we implement machine learning and AI, I want to show you the two main way we actually apply it, which is post-processing and the AI data-driven model. So what is the difference between those two? So for post-processing, we have a forecast based on a physics-based model, in this example, our Westworth model. Then from the past, we have prediction from the same model, and we also have observations from the past, so the quantity that we're interested in. What we do in the post-processing phase, we use machine learning to learn how the model has behaved in the past. So the machine learning actually can learn the biases and the conditional biases of the model. It can basically predict what kind of mistakes the model is going to do for today's forecast. So in a post-processing framework, you apply the machine learning correction to the physics-based model, and you further improve the prediction. And I will show you an example of that. Data-driven model, it's a very different framework. The way this model works, we have a reanalysis, for example, from the past 34 years, which is basically a reconstruction of the atmosphere by blending together first guess from physics-based models. So physics-based models are still part of the equations, and observations. But you could also use observation from the past, or as well as reforecast. But so far, most of the application has been based on using reanalysis. With that data, you can train that model that in real time generates a prediction. And so it's a very different way to generate weather prediction. And it's a bit, so let me dive into that. But sorry, before we talk about that, I want to show you what you can do with post-processing. So here's an example of correcting our 200-member ensemble with a deep learning algorithm for the prediction of precipitation, right? On the left, you're seeing the overall predicted skill as measured by continuous rank probability skill score. In that case, the higher the better. Here we're looking at, this was about 4-week period where the Western US was impacted by 9 consecutive atmospheric rivers. We call it atmospheric river families. It was a series of very impactful storms over the area. And so for CRPS on the left, you see that our 200-member ensemble in red is competitive with the European system prediction and is better for the first 4 days. It's better for every lead time than the US system. But then on the purple line, that's the deep learning on top of the 200-member ensemble. You see that it's using our 200-member ensemble as a springboard. It learns some of the mistakes that it does. And for the first 4 days of the forest, actually further improve the prediction. Now, as I mentioned to you, we really care about extreme precipitation on our center. And so that's what you're looking at, the 2 panels to the right. We're looking at a Braille skill score, a score to measure the quality of probability prediction. And it's a skill score, so the higher the better. And for predicting the probability of precipitation to be about 25 millimeters and be about 50 millimeters. And here you see there is even more separation. Now, our 200-member ensemble is better than both the European and the US system for every forecast lead time. And again, the correction with the deep learning of the 200-member ensemble further add prediction. And now here we're talking about extreme precipitation. Even more so for actually for the prediction of 50 millimeter, which is higher distribution. In our paper, we actually looked also at percentile of the distribution, the 95th, 98th, and 98th percentile, and we see similar kind of results. So great results here. For weather prediction, at least, we can do a lot for deep learning and better predict precipitations, particularly for extreme events. So now, let's talk about AI data-driven models. What they are basically, these models are learning how the atmosphere transition from one time to the next time step, typically with a 6-hour increments, and how a different set of variables evolve in space and time to the next time step. So far, most of these applications have been they've been trained using the European Center ERA5 reanalysis, which is a 25-kilometer resolution. And if you ask me, this is a revolution for our field. This is a very different way to do weather predictions. Let me tell you some of the key aspects of it. First of all, now we can do a weather prediction in a matter of a global weather prediction, multivariate, three-dimensional, in a matter of few seconds to minutes. With a physics-based model, you need a few hours on a very large supercomputer. That's the first point. The second point, they're actually as skillful, if not better, than the state-of-the-science physics-based model. And you can look up the literature, for example, that is ECNWF has done comparison with their IFS system, which is the physics-based with the AIFS. And they show that even for precipitation, actually, these models perform well, particularly for longer lead times. They do need a lot of computational resources to be trained. So that's a requirement, a limitation from most of the organizations that don't have access to that kind of computational resources. But once they are trained, you actually can generate a forecast very quickly. Another very important aspect is actually this model for the generation of real-time prediction, they use 5 to 10 times less energy. So that's another important aspect to keep, as long as we're talking about weather predictions. And let me show you why it's very important, why I think it's a revolution. Now, because these models are so fast, now we can generate many more ensemble members. I told you that with a very large supercomputer, we can generate a 200-member ensemble at our center based on a physics-based model. In this paper here, we actually developed a 540 members based on the ANF node, which is one of the models that's been developed by NVIDIA. And here you see an example of a prediction of atmospheric river. Those are different ensemble members. Well, we proven that, that actually this can generate very skillful prediction. And why is important? Because now, we probably, with this very fast simulation, we can generate maybe, 10,000 members. The question there is, how that's going to help us for the prediction of extreme events, right? Because that's what is really important, for example, for one of the applications that we really care about, that is the one that I show you about, the management of reservoirs. And here you see an example at Feather River Basin, which is a basin in Northern California, where these ensemble mean closely follow what was observed. So I think there is a lot of promise here, a lot of development. The other things we need to keep in mind that this model just came about, right? We're talking about 2 years, right? 2-3 years at most. They're based on algorithms been developed over maybe 5-10 years, but the actual model came the last 2 years. So we're just scratching the surface here. Physics-based model has been around for 40-50 years. So I think there is a lot that can be done here now, and we're just scratching the surface. Another very important aspect, something that we heard from other speakers during this symposium, is the fact that we rightfully asking is, are these models learning the physics, right? And here is an example of a work that just been submitted, led by our postdoc, Jorge Baño Medina, where basically what we're doing here, we're comparing the sensitivity compared with a physics-based model from a paper that was led by Jim Doyle, 2014. And we're comparing that with the sensitivity calculated with the SFNO, the spherical Fourier neural operators, which is one of the models made available and shared with the community by NVIDIA. And if you ask me, these results is remarkable. So what we're looking here, those are sensitivities. So those are sensitivities of the humidity field in the shaded color of the perturbation of the kinetic energy in the Bay of Biscayne, close between France and Spain. So basically, you perturb kinetic energy in that area, close to Spain and France, and then you want to know what is the impact of 36 hours earlier in the model on humidity field, right? And here, that's what you get from a physics-based model. By the way, I should say, we should not expect the same thing here, because these two models are different variables, different vertical and horizontal resolution. But qualitatively, the model, it's, by the way, those are sensitivity over the black line there between the two dots, right? So it's upstream where the actual storm was 36 hours before the landfall. So this model is actually recognizing the fact that perturbing the kinetic energy close to Spain and France has an impact on humidity several hundreds of kilometers upstream. So it's actually learning the physics. And the way I see it is, it's half full glass, right? They are learning the physics. We saw the example of the, one of the speakers this morning was talking about, the paper that recently came out led by Massimo Bonavita at ECNWF, where there were some concern. But the way I see it, there is a lot of promise here. They're actually learning the physics, or at least part of the physics. And this is my last slides. Thank you.
Thank you. Are there any questions for our speaker? Okay.
Thank you for a great presentation. Regarding the last part, AI-driven models, I can see that you rely on the FNO. My question is there a specific reason you chose this type of neural operator? There are many out there. Did you test any others? Did you compare them? Or just you went with FNO?
The reason is very practical. When we wanted to start investigate this kind of model, this one's the only publicly available. Now we're also looking at GraphCastNet. We actually have a collaboration with ECNWF that developed a regional version of it. But we started with this because we're talking 18 months ago or so. This was the only one publicly available. Now there are actually 4 or 5, I think. So it's very, very practical reason.
Thank you.
Yeah.
Hello, once again, I want to thank you for the presentation. My question is, how would AI models like this affect practices like geoengineering?
That's a great question. Well, I would say similarly as the physics-based model have in the past. So this model, basically the claim I'm trying to make here, they look pretty similar to what you can get from a physics-based model. Some aspects are better, some aspects are worse, but we're talking about very similar tools. And so the way these models are used, physics-based model, but also this could be used for cloud engineering, for example, for cloud seeding purposes, can help us improve the operations. We actually have a project with the UAE Rain Enhancement Program, and Youssef is the program manager of that program, and where we are exploring new machine learning technique to try to identify what are the best region and the best time to seed clouds to generate precipitations. So I would say these models can be used similarly as physics-based model being used for these purposes.